All right, let's start looking at some of the more kind of advanced integration rules here. So the first one we're going to see is this constant multiple rule. So what this really does is it tells us how to integrate when we have a constant k times a function f of x. And there's a constant, we have a constant multiple here. So k is a constant and we're multiplying our function f of x. And so really what this rule says is this constant multiple, this constant k, we can think of it as really just bringing out that constant k, bringing it out in front of the integration sign. So that's what really this rule says. And so if we were integrating constant k times f of x, another way to do it is to first integrate f of x, focus in on those variable parts, get the antiderivative for them, and then just multiply your result by k. So we can move the constant k outside of the integration sign. That's what this first property rule says. All right, so it's important to note here, k needs to be a constant. So if k is a variable, this property wouldn't work. So a quick note here, but this is important. If we were going to integrate x times x squared, we wouldn't be able to take this x outside of the integration. So you cannot move variable terms outside of the integration. Variable terms are kind of stuck in between the integral and the dx. But if you have a constant, multiple, those can be moved outside. So this is very important. It's easy to make this kind of mistake. But if we have variables in between the integral and dx, think of those as just kind of like bookends. If we have variables in between, those variables have to stay in between. We can't move them out in front of the integration. All right. So we also have what we call the sum rule. And what this says is if we have two functions, f of x plus g of x, and we want to calculate their integral, their antiderivative with respect to x, well, what we can do is we can just focus in on the first function, get the antiderivative for that, so find the antiderivative of f of x. Then we can focus in on just that second function, so get the antiderivative of just g of x, and then add those two antiderivatives together. And so this way gives us a way to kind of break up our functions based on wherever we have plus or addition or subtraction signs. So that's what this one is saying. We can split up the integration. At plus or minus signs. And together, if we take these, we call this the sum rule, but really this also works if we had a subtraction here, because we can really think of subtraction as just multiplication by constant -1. So, the sum rule here works if this is a plus or a minus. So if we take these two rules together, the constant multiple rule with the sum rule, a lot of times we call this term by term integration. Just like what we did with derivatives. So the overall process is going to feel fairly similar. When we have a polynomial, we're just going to look at each term of our polynomial and get the antiderivative. Just like we would do with derivatives. We would just look at each term of our polynomial and differentiate. So we're going to call this process term by term integration here. So let's try an example. So let's look at a few indefinite integrals. And what these all are, these are all constant multiples of a power function. And so that's the idea here. When we have these types of terms, what we want to do is we want to try to rewrite them or get them in this form of a constant times a power function. So we're always looking to try to rewrite our functions in this form, if possible. So if we look at the first one here, this one's already good. It's a constant 2 times power function x raised to the power 5. We can just kind of get right into integrating this. And so what the constant multiple rule says, this 2 is a constant multiple, what we can do is we can bring that 2 out in front and just worry about integrating x raised to the power 5. So this x raised to the power 5, this becomes just a power rule problem. And then once we have this result, we can just multiply the result by 2. So how does that look? Well, x to the power 5, we're going to use power rule. So we keep our variable the same. It's going to stay in x. Our old exponent is 5. We're going to add 1, so that's going to bump us up to 6. We're going to take this new exponent, flip it, put it in front, so it'll be 1 over 6. And that's our antiderivative of x raised to the power 5. And then we're going to multiply that result by 2. And because we're doing an indefinite integral, that's not quite the end of the story. We put our plus c on at the end. And then if we clean this up, we get 2 divided by 6 is 1/3. So we get 1/3 x raised to the power 6 plus c. So what we did right here, this is where we use the constant multiple rule. And generally speaking, we don't show this step normally. Normally this is a step that we just kind of do in our head. So, you might want to show this as you're starting to practice these integration problems, but once you get the hang of it, you're probably going to go right from the integral, maybe to this step, maybe right to the answer. So we generally don't show this step in our work. All right, so let's try 4 over x cubed. Let's get the antiderivative of that. And so when we have a fraction, variable term in the denominator, again, we want to try to rewrite this in this form, constant times a power function. So to start this off, I would rewrite this as 4 times 1 over x cubed. And then that 1 over x cubed, it's a fraction, so use a negative exponent. So I'd have 4 times x raised to the negative 3. And so this is a good form for actually getting the integration. Just like if we were going to do the derivative, I would want my function written like this because I could do the derivative that much easier. So same thing with integration. We want to try to rewrite it in this form, constant times a power function. And so how this is going to look is we don't normally show this constant multiple rule step. We normally kind of do it in our head. So one way to kind of think of it is just look at the variable piece here. Look at that power function part. Get the antiderivative. So let's do that. Our variable is x. Let's add 1 to the exponent. So we're going to go from negative 3 up to negative 2. Let's take this new exponent, negative 2, flip it, put it in front. And we had a 4 there already, so the 4 is going to stay in front as well. So what we've done is this 4 is just a constant multiple, so it kind of just sticks around. And what we've done is we've focused our attention on this variable part, and we just got that antiderivative. And then we throw on our plus c at the end. Now it's fine if we want to leave it like this. Probably better, though, to try to simplify. So 4 times negative 1/2 is negative 2. So there's our antiderivative. All right, let's try another one. Let's do this 5 times cube root of x. Let's find the antiderivative of this. And again, we want to try to write it as a constant times a power function. Right now it's a root function. We know what to do with root functions. Let's write that as x raised to the 1/3 power. It's the cube root. We'll write that as x raised to the 1/3 power. All right, so what do? Well, this 5 is just going to stay in front. And we're going to worry about getting the antiderivative of x to the 1/3. All right, so our variable is x there. Let's add 1 to the exponent. So 1/3 plus 1 is going to be 4/3. Then we take this new exponent and we flip it. So 3/4 is going to go in front of the x there. Kind of sandwiched in between the 5 and the x. And then we throw on our plus c. And probably good practice to just try to simplify this by multiplying these constants together. And if we do that, we get 15/4 x raised to the 4/3 plus c. And there's our antiderivative. And just in case you didn't see it, how we got this 4/3, it was 1/3 plus 1. Write that 1 as 3/3, and then adding the numerators gives us 4/3. So it doesn't hurt to show this if you have like these fractional exponents or even negative exponents. Sometimes this is helpful, but you don't have to show this in general. All right. So a little bit of practice using the constant multiple rule. Now let's try out, kind of expand the types of functions we can integrate, and let's see how the sum rule kind of works into this. And so what we can do is, when we look at this, we have the function 2x raised to the power 7 plus 6x plus 5. We're going to integrate this function. And, well, we're going to do it 2 ways. We're going to first just kind of showing all the rules. So way more work than we would ever really show. And then we'll just kind of do it the quick way, which is once we get the hang of this, it's how we're really going to do it in practice. So let's start by just kind of showing all the rules. So the first thing we can do is where we have these plus signs, we can split up the integration. So we can use our sum rule a couple times. So we'll get the sum of 2x raised to the power 7 dx plus the integral of 6x dx plus the integral of 5 dx. So that's where we use the sum rule. Okay. Then we can use our constant multiple rule. So we can take the 2 out in front. We can take the 6 out in front. If we wanted to, we could bring the 5 out in front and there would be just a 1 left over here. But I think it's easier just to leave the 5 there. And so what we've done here, this is the constant multiple rule. So for all of those pieces where we had a constant multiple in front, we're able to bring those out in front of the integration. And then what we do is we just go through, and each of these now, this integral here is power rule. This integral here is power rule. And this integral here, we're just integrating a constant function. So we know these are kind of two of our building block forms. These are two of our kind of most basic antiderivatives. So we can just do them. So we're going to get, let's start with this x to the 7. What does the antiderivative look like there? Well, the variable is x, or the variable is x, so we keep that the same. We add 1 to the exponent, so we go from 7 up to 8. And then we take this new exponent, 8, and we flip it and put it right in front of the x. So 1 over 8 times x raised to the power 8. And then we're going to multiply by 2 because that 2 is in front. We go on. So we want to integrate x. And there's kind of a hidden exponent here. there's a hidden exponent of 1. So when we do the power rule on just x, our variable is x. There's a hidden exponent of 1 there. So when we add 1, it's going to bump us up to 2. We're going to take that new exponent. We're going to flip it. So it'll be a 1/2 in front. And then the 6 is a constant multiple. So it just multiplies in at the end there. And then finally, we want to integrate 5, the constant function 5. And we know how to do that. It's just 5 times x. And now technically, each of these individual integrals here would have had their own constant. So there would have been some kind of constant plus c from here, maybe a different constant, another constant from here, and another constant from here. But if we take all these different constants and add them together, it's still a constant. So we end up just saving that plus c until the very end, and we'll just put 1 plus c at the very end here. So technically there would be an arbitrary constant for each of these, but if you have 3 different arbitrary constants, you could just group them all together and say, okay, here's one big arbitrary constant at the end, and that's what we're doing. So cleaning this up, we get 1/4 x to the power 8 plus 3 x squared plus 5x plus c. Just cleaning that up. Now this is way more work than we would ever show. So when we're doing these integrals, we're not really going to show the sum rule very much. And we're not going to show the constant multiple rule very much. These are 2 rules because they're on the easier side. We don't generally show them. So normally what we would do is, given the integral, so if this is the integral we're trying to do, we would probably jump either right to here and just get to it, or you might even just jump right to the answer. So kind of like what we've seen with some of our more basic derivatives. Once you get the hang of some of the rules, you're probably going right from the function to the derivative. Same idea for these indefinite integrals. You're going right from the integral here, either right to the answer or just about right to the answer. Okay. So next we're gonna try a few more examples like this, just to get practice of how these things look, when we're doing them without showing all these rules. So we'll see that next.